Hello class, welcome to lecture 16. So today we're talking about sample proportions. Um, Previously we were talking about sample means and all sorts of stuff to do with that. So today will be very similar, just sort of a different type of problem, but the previous knowledge will help us. Okay, so let's get started. So next we study proportions as opposed to means. So I'll give you an example of a proportion in a second. But you should sort of compare them to means because we're going to do the same stuff we did. But now for proportions, so the idea is that this is going to be a new parameter, a new number associated to a population. And just like we had a mean as a parameter of a population, then we took sample means, and now we're going to look at sample proportions. So we're going to study proportions and sample proportions as opposed to means and sample means. But it's good to keep the comparison going as much as possible. So then this is a statistic because it's a number associated to a sample instead of a population. Okay, so first of all, let's just see an example of a proportion. What do I mean by a proportion? Because I have used the word proportion in other contexts, but it's a little bit different in this context. So a proportion now is something like this. So for example, you could take a poll, and so you're taking a poll of 1,200 people who vacation during summer. And then you might ask them a question and see what proportion of them answer a certain way. So the poll asked if they would work during the vacation. So in this situation, 552 said yes. So that's a proportion. 552 out of the total amount, 1,200, answered a specific way. So this is a proportion. And it's actually a sample proportion, and then you could put it as a decimal if you'd like. So this is an example of a sample proportion because it's coming from a poll. So it's not coming from a whole population, it's coming from just a sample of 1,200 people. And so what we do is we call it P with that little hat on top, little P with a hat on top. And that's notation that's going to keep coming up later. So P with a little hat on it is a sample proportion, whereas no hat, just the letter P, is always going to be the actual proportion. It's very similar to the bar notation that we used for means, but now we use hats instead of bars, just to make things more confusing. Okay, so now we're going to do the same kind of stuff we did last time with sample proportions. Sorry, the same thing we did last time with sample means, but now for sample proportions. So let's do an example that displays what's going on. So here's how it's going to go. So the idea is that you're going to be given or assumed an actual proportion. So here's a situation where we're doing that. So somebody else has previously figured out statistics, the population proportion. So according to the National Center of Health Statistics, so in this case, they are telling you the population proportion, 15% of all Americans. So here the population is the American population. So we're just talking about Americans, have hearing trouble. So this is being told to us, so this is being assumed for us. So what we can say about the information we've gotten so far is that the population is Americans, and the proportion that we're looking at, the proportion that have some property that do something, which in this case is have hearing trouble, is called little p, and it's 15%, but we're going to write it as a decimal so that it's an actual proportion, not a percentage. So that's what we can say from this information. And again, a proportion is a type of parameter, an example of a parameter, because it's a number associated to a population. Okay, so that's the kind of information you'll get in a question. You're given a proportion, and then you're going to be asked about samples. So then I might say something like, in a random sample of 120 Americans. So now we're just asking a sample of Americans, not the whole population. We can ask about probability of that sample being a certain thing. So what is the probability that, so now we're going to ask about a sample proportion. So we're going to ask about, what's the probability that your proportion is 12% or less, given that the actual proportion is this. So it's very similar to the previous problems where it was like, given that the mean is something, what was the probability that the sample mean was less than something or more than something or something like that. Very similar. Okay. Good. So what this is really translating, what we're going to translate this into to sort of compare it to last time, we're really asking us to find the probability that a sample proportion, so a little p hat, is to the left of 0.12 on some normal distribution that we haven't yet said what it is. But there's going to be some normal distribution for capital P hat, which is having to do with sample proportions. Okay, so I'll fill this in later, but I'm just comparing it to previous stuff. So really this in fact should be a capital P hat to compare it to capital X bar. And this is a little specific P hat to compare it to little X bar from last time. So there's got to be some normal distribution that we can look at where we don't know these things yet, but we'll fill all this in a second once we get the idea. And then 0.12 is on here somewhere. I don't know where, but pretend it's there. And we're finding this area. And then that's going to just be saying, okay, well, we got to find the z-score for this specific sample proportion and then use that calculator to get area to the left. Okay, so we got to figure out this distribution that we're looking at. And that's the goal for now before we actually tackle these types of problems. So again, figuring out the normal distribution is sort of the more theoretical part, but then doing the actual problems won't be so bad. Okay, so here's the idea. Given a population proportion P, so that's just given to you in the previous example is 0.15. The idea is if we take all possible samples and we get all those proportions that we get from those samples, then once again, just like with sample means, we get a normal distribution. And that's the mystery normal distribution up there. For this big p hat, which is sample proportions. And big p hat takes possible values little p hat according to this normal distribution. And so what is the normal distribution going to turn out to be? Well, I'm just going to have to give it to you because to actually figure it out takes some very fancy math, but it's going to have, because it's a normal distribution, it has a mean and it has a standard deviation, but it's the mean for sample proportions. So we're going to call it mu with a little subscript again, p hat, and standard deviation is also for sample proportions. So we're going to call it sigma with a little p hat as a subscript also. And that's what tells us the middle. And that's what tells us the inflection point to the right and to the left by adding one standard deviation and subtracting one standard deviation. But what are these numbers? Well, they're going to turn out to just be the mean will just be the exact same proportion that you're given. And the standard deviation is a little bit more complicated. So just to remind you, this is the given population proportion. So in the previous problem, it would have been like 0.15. And the standard deviation is a bit more complicated. It's the square root of that same proportion times 1 minus that proportion divided by the sample size. And that's all under a square root. So that is the standard deviation for this normal distribution. And then all our questions are just asking about areas for this normal distribution. Okay, so we use this to answer questions like just sort of how we've seen before, find the probability or maybe percentage or something like that, but I'll just keep it as probability. Find the probability that a sample of some amount of people or whatever population you're studying has a sample proportion. So a sample proportion, those numbers live on the x-axis here with probability according to this distribution. So then you always ask something like, what's the probability that a sample that you get has sample proportion less than or more than, greater than, however you want to say it, or between blank. And then it's really just the same as finding the area on this distribution I drew up there. Finding the area below or above or between blank, whatever it happens to be. And then this is just finding z-scores again and using that calculator. So we're just finding the z-score for the sample proportion, or if there's two to look at between, and then getting the area using that same calculator. Okay, so it really just becomes like the problems last time with a different start. Okay, so now we'll do an example. All right, so we're gonna use that same example from earlier. So I already wrote it down, but I guess I'll write it again. So according to the National Center for Health Statistics, 15% of Americans have hearing trouble. And we're going to answer a question about a sample. So in a random sample of 120 Americans, what is the probability that at most 12% have hearing trouble? So just translating this question, we really want to find the probability that capital P hat, the sample proportion, is less than 12%, or really 0.12. And this is your specific P hat, little P hat. Okay, so we're going to use the normal distribution that I claim automatically exists, where the mean is just the given population proportion, which in this case is 0.15. So that's where this 15% is coming into play. This is the population proportion, or at least it's telling you the population proportion is 0.15. And the standard deviation is this slightly more complicated formula. So it's going to be 0.15. Well, let me write the equation before I use it. So it's P times 1 minus P over N, all under a square root. So it's going to be 0.15 times 1 minus 0.15 divided by the sample size in this problem is 120. So I'm taking a sample of size of 120 people. That's how that 120 is coming about. You plug this in a calculator, you should end up with 0.0325, roughly. So what we're looking at is this normal distribution. And we're finding the area underneath it to the left. Or you could think of it as being below a specific value, 0.112, on this distribution here that I just found the mean for. So the mean is 0.15, and the standard deviation was 0.0325, so I have to add that to get over here, and then I have to subtract that amount to get over here. So this is really, I'm just adding 0.0325, and I'm subtracting 0.0325 because that's the standard deviation for this normal distribution. And so where's 0.12? 0.12 be around here somewhere. So I'm really finding the area below it because I want to know the probability that at most, which is another way of saying less than, at most 0.12 of the sample has hearing loss. So to find this area, now I need the z-score on this normal distribution for 0.12. And it's still the same z-score formula as always. So it's your value that you're looking at minus the mean of the distribution divided by the standard deviation of the distribution. Same formula as always. Whatever your mean happens to be in your problem, and whatever your standard deviation happens to be in your problem, it's these two things. So if you calculate this, you'll get negative 0.92. And then you can turn that into an area to the left using that same calculator. And you'll get 0.1788. So that's the blue area here. So now to actually answer the question in context, the probability of selecting a sample of 120 Americans, I guess it's always a random sample, I should be clear, random sample, where at most 12% have hearing trouble, is this probability that I just found. Okay, so that's it. So we can do other types of questions that are very similar and try to answer them too. All right, so we'll keep using this hearing loss thing. And we'll ask a different question about it. So suppose a random sample, we'll still use the same sample size, so we can use the same exact normal distribution. So suppose you got a sample and it resulted in 26 of the 120 with hearing trouble. So this time they're not giving you the sample proportion immediately, but they are telling it to you. You just have to calculate it. And then the question is a bit more vague. So what might you conclude about the sample? So it's a bit more vague. It's not asking you directly for like a probability, but it really is. You just have to see that that's what it wants you to do. Okay. So first off, this time we have to figure out p hat. but it's not so hard. They're not telling you 0.112 like they did last time. Instead, they're telling you a specific amount of people out of the sample. So that's how you get your sample proportion. So you want to see what 26 out of 120 actually is. In this case, it's 0.217. And then we want to conclude something about getting such a sample. And that really just means like we want to see if it's weird. Is it very far away from the mean, or is it sort of fine to get such a sample? So that's the idea when they ask you a vague question about what you might conclude. Okay, so to conclude something, about the sample, we need to see how unlikely such a sample would be, or how likely it would be either way, to get such a sample. Or because it's so high above 0.15, which is the mean, or we want to see if it's bad by seeing how unlikely it is to get such a sample, or worse, or above it, because it's far above the mean. So what that means is we're translating this into an area problem again, but now it's going to be area above. So what we're really doing is we're finding the probability that capital P hat is above, or to the right of, is above the sample proportion, the specific sample proportion, little p hat, 0.217. So we're still finding the area on the same normal distribution because the sample size is still 120. I can use the exact same distribution as before. But now I'm looking at 0.217. And I'm finding this area. But now it just becomes a problem like we're used to doing. So I just get the z-score for this specific data point, 0.217, on this distribution, using the same formula as always, 217, whoops. 0.217 minus the mean divided by the standard deviation. Which was 0.0325. And if you get that, you'll get 2.06. So then you can turn that into an area to the left using that calculator, and you'll get 0.980, but I really want the area to the right. And that'll be done by subtracting from 1, because the total area is always 1 underneath the bell curve, and that'll be 0.02. So to answer the question in context, what is this really saying? Saying that there's a 0.02 chance of getting a sample like this or worse. So I would say it's unlikely. It's only a 2% chance. Pretty low chance. Okay, so we're going to do another example in 1 second. Okay, so now we are going to find, we're going to do an example where we find probability between two places. So here is an example We're using the same distribution still, but now let's find the probability of getting a sample proportion between 0.12 and 0.217. So we already found areas to the left of both of these. So this is really just an example of how to find area between two things. We already did all the hard work. So we're still on the same normal distribution. 0.12 is around there. 0.217 was around there. So now we're trying to find this area. And we already found this red area. That was the probability of being to the left of 0.12. And we already found this green area. That was the probability of being to the left of 0.217. So all we got to do is subtract those two areas to get the area in between, the blue area. So this green area was 0.980, if you remember from earlier. The red area was 0.1788. So now the area in blue between these two sample proportions, these two, you could think of this as two p hats, p1, p2, and we already found all the z-score stuff earlier in the earlier parts of this problem, and then we just turn them into areas to the left. 0.98, sorry, this one was 0.980 because it's P2. So Z2 goes with that one. And Z1 is 0.788. Sorry, that's not Z1, but that's what Z1 turns into, the area. So you can go scroll back and look at that work to get those z-scores again if you want. I guess I'll just write them here. What were they? So this one was 2.06, and the other one was negative 0.92. Okay, so common mistake is as people subtract the z-scores, but no, you subtract the areas. Okay, so then finally the area between the two is 0.0812, just by subtraction. So the answer is that the probability of getting a sample proportion, we're still working with sample size of 120 because that didn't change during this whole problem, between 0.12 and 0.217 is 0.8012. Okay, so in this situation, there are some other things we have to worry about that I've sort of glossed over. But the idea is that there's like secretly high-level math in the background, and what this means is you actually can only use this stuff in certain situations. So this only works, the math we've just done, if you have to actually check these conditions. So you have to multiply n times p times 1 minus p, and you have to check that it's bigger than or equal to 10. And you also need to make sure that n is not too big. So it's less than 5% of the population. So it's sort of counterintuitive, but actually having too big of a sample is bad. It'll break our ability to use this stuff. So this is really just saying sample is not too big. And this first condition is actually just saying you have to make sure your sample is not too small. It's got to be just right. And then once you do this, you can do all the math we just did, once you make these checks. So in the example we just did, I can do this check real quick. The sample size was 120. The population proportion was 0.15. So if I multiply this out, it'll turn out to be around 15.3, which is bigger than or equal to 10, so we're good. And 120 is definitely, don't even have to check this, you just have to say it. It's less than 5% of the population of the US. Because in this situation, the population was total number of Americans. Yeah, so we're good there. Okay, so this is the end of the examples. Now I just want to do a little summary comparison thing between what we just did and sample mean stuff. So the idea is that we use capital X bar to mean the sample mean, and we use capital P hat to mean sample proportion. And then for sample mean problems, you're given something, you're always given a population mean, and that's mu, and you're given a population standard deviation, and that's always called sigma. But then for sample proportion problems, you're just given, you're given the population proportion. And that's called little p. So then in both situations, what you do next is you take a sample, or you're told that there's a sample of some size n, and that's the same over here. In both situations, you do that. And then now we build the normal distribution. So what that means is we have to find the mean of X bar, and we have to find the mean of P hat. But it's always nice and easy because the mean of the sample mean, sounds weird to say, is just the mean of the population. So you're really just using this number that's already been given to you up here. And the mean of the sample proportions is just the population proportion. So you're just using this number here. And then, so that's the mean of the distribution that you're using to answer the questions, but then you also need the standard deviation of these things to build the normal distribution. And that comes from, on the left, the notation is that it's called this thing, sigma sub X bar, but it's just found by using the standard deviation that they give you and dividing by the square root of n. But for sample proportions, it's this slightly more complicated formula. Standard deviation is the square root of p times 1 minus p over n, all under a square root. And then that gives you the standard deviation of the normal distribution that you're using to answer questions. So now you have the mean and the normal distribution, or the mean and the standard deviation, so you can then translate whatever question that you're looking at into finding area under this curve, where now we know the middle, that was previous step. We also know the first standard, we know the standard deviation, so we can find these inflection points. And then same thing happens over here, but it's a different normal distribution, but we're still just finding area, but it's just a different one. So this one is found by using the numbers on this side. So the mean we know from up earlier, then we add the standard deviation and we subtract the standard deviation. Uh-oh, my screen sharing disappeared. What happened? Okay, well, the notes will have it written down anyway, so hopefully this isn't too bad. But anyway, this is the finished product there. Okay, so it's very comparable types of problems. All right, so that is it for today. See you next time.